Is it possible that a black hole isn't actually a celestial object? That it's neither the end of a star nor a force of cosmic mystery, but something else entirely? Like a running program, a compressed system hiding the underlying truth of the universe? You can throw anything into it, and it will only give you back three values: mass, spin, and charge. No more, no less. As if it were a pre-designed formatting template. It's not just compression, it's more like a complete wipe, erasing all details, like the universe clearing its cache. What's truly unsettling, though, is that physics tells us this information might not be gone at all. It could still exist, hidden along the boundary of the black hole, concealed behind dimensions we can't even begin to understand, places beyond our current imagination. So today, the discussion is not about how terrifying black holes are. It's about something much deeper. A question so profound it could shake the very foundations of physics. Does information truly disappear from the universe? In our time, we're no strangers to the term black hole. But if we rewind the clock 300 years, we find that this enigmatic phenomenon began with a surprisingly simple question. How strong must gravity be to prevent even light from escaping a planet? And this question didn't come from a renowned scientist. It came from John Michell, a rural English clergyman. He wasn't gazing through telescopes or tinkering with lab equipment. He simply used Newton's formulas and reasoned quietly on paper. He proposed that if an object's escape velocity exceeds the speed of light, then not even light could escape from it. Such a body wouldn't explode or break apart. It would simply disappear, like a light bulb permanently switched off, leaving not even a trace behind. What's even more fascinating is that Michell provided a detailed logical framework for his idea. Look at escape velocities. Earth's is about 11.2 kilometers per second, the Moon's is 2.4 kilometers per second, Jupiter's is nearly 60 kilometers per second, and the Sun's reaches 617 kilometers per second. If an object's mass were infinite or its density immeasurably high, its escape velocity could theoretically exceed the speed of light. Thus, Michell predicted a terrifying kind of object, a dark star from which even light could not escape. It sounds remarkably similar to our modern idea of a black hole. But at the time, no one paid attention to his theory. In the 18th century, humanity hadn't even figured out what light truly was. Newton believed light was composed of particles, but no one could confirm whether it could be pulled back by gravity. And so, Michell's idea was buried, filed away in the drawer of forgotten science, where it would remain untouched for the next 150 years. As we entered the early 20th century, a revolution swept through the scientific world. Albert Einstein proposed the theory of general relativity, completely overturning humanity's understanding of gravity. He revealed that gravity is not a force in the traditional sense, but rather the curvature of space-time caused by mass. You're not being pulled to Earth. You're simply following a naturally curved path in space-time. This way of thinking was a shock to the scientific community at the time. But there was a problem. No one knew how to solve the highly complex equations Einstein had introduced. That is, until the First World War, when a German officer named Karl Schwarzschild, working from the trenches, managed to derive the first exact solution to Einstein's field equations. The result was astonishing. It suggested that if a massive object were compressed within a certain critical radius, it would form a boundary, a point of no return where even light could not escape. This boundary would later be known as the event horizon. And beyond that horizon lies a region where the laws of physics, as we know them, cease to function. In simple terms, the equation Schwarzschild solved on the battlefield gave mathematical confirmation to John Michell's old idea. A dark star from which light cannot escape wasn't just science fiction, it was a real, predictable consequence of general relativity. But the story doesn't end there. When general relativity and the Schwarzschild solution were first introduced, most scientists thought it was just a mathematical curiosity, like a kink in a graph, strange looking but not physically real. At that time, mainstream physics was obsessed with quantum mechanics. Black holes? Nobody cared. Even famous figures like Richard Feynman mocked the study of gravity, once joking that gravitational physicists were wasting their time. Yet science is not a popularity contest. Just because no one is paying attention doesn't mean something isn't real. Black holes waited silently in the wings for their moment of vindication. From Michell's speculative calculations on escape velocity to Schwarzschild's equations scribbled in a wartime trench, this part of scientific history was nearly forgotten. But it planted the seed of something explosive, something that would eventually be triggered by chilling astronomical data in the 1960s. At that time, astronomers detected strange, high-energy X-ray signals from regions of the sky that appeared completely empty. These objects didn't spin, didn't twinkle, didn't emit visible light, yet they behaved like cosmic whirlpools, tearing apart and devouring nearby stars. You couldn't deny their existence, but you could never quite see their face. Suddenly, the once ridiculed idea of a black hole became the only explanation that made sense. Black holes, it turned out, were real celestial objects. Thus, the concept of the black hole finally began its journey out of mathematical theory and speculative imagination and into our actual universe. But there was still one big problem. Theory alone was never enough. You could draw a perfect event horizon on the blackboard, but that wouldn't convince skeptics. Do black holes really exist? Are they physical entities in the cosmos, or just dazzling illusions created by mathematics? It was at this moment that two names entered the annals of history: Stephen Hawking and Roger Penrose. This legendary duo used a series of geometric techniques and space-time diagrams to push Einstein's general relativity to its very limits. They shifted the focus away from isolated black holes and asked a much broader question: what happens when a large mass of matter collapses somewhere in the universe? The result was astonishing. They proved that, under very general conditions, as long as matter is compressed densely enough, it will inevitably form a region that encloses a singularity, what we now call a black hole. Not a possibility, a certainty. Even more remarkably, their proof didn't rely on any assumptions of symmetry. They didn't need to presume a perfect sphere or a neatly formed planet. Their theorems revealed something fundamental. Once you push matter beyond a certain limit, gravity will rip space-time apart and create a black hole. No exceptions, no loopholes. It was as if the universe had a hidden rulebook. Trigger the right conditions, and black holes will appear, automatically, unavoidably. Yet all this was still theoretical. The real breakthrough came from the sky. In 1971, American astronomers, using an X-ray telescope, focused their attention on a mysterious patch of the sky known as Cygnus X1. This region emitted intense X-rays, yet no visible light. Stranger still, the X-rays were not steady. They flickered and pulsed, as if being torn out by an invisible force. Further investigation revealed that this high-energy radiation came from an unseen companion star. This hidden object was violently devouring material from its neighbor. It wasn't a normal star, it had no surface, it gave off no light. All it left behind was a dark abyss, relentlessly consuming everything around it. In that moment, the black hole stepped out of the realm of theory and into reality. Not imagined, but captured in an X-ray image. And that was just the beginning. Decades later, the US-based LIGO Observatory delivered another seismic moment. It detected gravitational waves, ripples in space-time itself, created by the merger of two black holes. These waves traveled billions of light years and still managed to be detected by our instruments on Earth. It was the equivalent of two invisible monsters colliding in the depths of the cosmos, roaring and crashing into each other. The resulting shock waves rippled through the fabric of the universe, eventually reaching Earth as the faintest tremor. So now, we're no longer asking whether black holes might exist. They do. At that moment, we didn't just see black holes, we heard them merging in the depths of the universe. From Cygnus X1 to the gravitational waves captured by LIGO, humanity experienced something extraordinary. For the first time, black holes were no longer silent theories or distant predictions. They became real, roaring presences. We had moved from chalkboard equations to cosmic echoes. Black holes had finally stepped out of abstraction and into reality. They were no longer the ghosts of physics, but some of the most powerful and undeniable entities in the universe. But just when we thought we were beginning to understand them, a new and deeper mystery emerged, one that left scientists more perplexed than ever. Why is it that these extreme celestial objects can be completely described using only 3 numbers? This question challenged everything we thought we knew. Astronomers were stunned to discover that no matter how a black hole formed, whether it came from the collapse of a supermassive star, the merger of 2 smaller black holes, or even in a thought experiment where an entire library, every database, or the total knowledge of a civilization was thrown into it, the black hole would always be described by just 3 quantities: mass, spin, and charge. Everything else appeared to be erased, as if the universe had run a cosmic formatting function. At first, some believed this strange simplicity was just a coincidence, perhaps a feature of a few special solutions to Einstein's equations. After all, general relativity is notoriously complex, and one might expect a wide variety of possible outcomes. But no matter how the equations were manipulated, only a limited number of black hole models ever emerged. The first was the Schwarzschild black hole, which has mass but neither spin nor charge. Then came the Reissner-Nordström black hole, which added charge. After that was the Kerr black hole, which rotates. And finally, the Kerr-Newman black hole combined all three parameters. Still, many scientists were reluctant to accept that black holes could be so clean. They believed these cosmic monsters should be more complicated, more expressive. Dozens of new models were proposed, but none could escape the gravitational pull of the same three parameters. Eventually, physicists had to accept a strange but undeniable truth. Black holes in our universe obey an odd rule. No matter how they are formed, in the end, they retain only mass, spin, and charge. This discovery became known as the no-hair theorem. The phrase captures a simple but profound idea. Black holes have no external features. They have no distinguishing marks, no expression, no complexity visible from the outside. They don't wrinkle, don't wear scars. You cannot tell whether a black hole swallowed a star or an entire library. They all look exactly the same. And that's what makes this so eerie. Because everything else in the universe is full of detail. A single star is a rich storyteller. Its temperature, its fusion process, its magnetic field, its stage of life, all of it reveals its unique journey. Even a tiny asteroid carries the evidence of a long and winding history. But black holes, they tell us nothing. They erase the story. Even asteroids, when struck by meteors, carry unique dents and craters, marks that record their histories like stories written in stone. But black holes remain completely silent. They show no signs of what they once consumed, no traces, no stories. So where did all the information go? Did the details of everything that fell into a black hole get erased forever? Or are they hidden somewhere beyond our reach? Some scientists began to suspect that black holes might not just trap matter, they might also destroy information. But this idea challenges the core of modern physics. In quantum mechanics, information is never truly lost. It might be scrambled or hidden, but it always exists. That's why black holes pose such a troubling question. If all we're left with are three numbers, mass, spin, and charge, what happened to everything else? This mystery puzzled scientists for years, but then came a surprising discovery. Black holes have entropy and temperature. We used to think black holes were the coldest, most lifeless places in the universe. No light, no sound, no activity, but in fact they behave like thermal systems, like boiling water or hot gas. They have energy, and they can radiate heat. Even stranger, a black hole's entropy doesn't depend on its volume, but on the area of its surface. That means all the information might be stored not inside the black hole, but on its outer boundary, its event horizon. This idea sounds strange, but it has deep meaning. To understand it, think of air in a room. You feel temperature and pressure, but you can't see each air molecule. Yet the air is full of tiny particles, each with its own motion and energy. The number of ways these particles can be arranged is what we call entropy. Entropy is a measure of how complex or disordered a system is. The more possible arrangements, the more entropy it has. So here's the paradox. Black holes seem simple. They're described by only three values, but they also have incredibly high entropy, meaning they contain a huge amount of hidden complexity. Physicist Jacob Bekenstein was the first to take this idea seriously. He dared to ask, how can something so simple hold so much information? During a conversation with his advisor John Wheeler, Jacob Bekenstein posed a puzzling question. If you pour a cup of hot tea into a black hole, what happens to the information? All the molecular arrangements, the temperature distribution, does it all vanish forever? If the answer is yes, that would be a serious problem, because it would mean violating the second law of thermodynamics, which states that the total entropy of the universe must always increase. It cannot decrease, ever. This isn't just a minor rule, it's one of the pillars of physics. The renowned physicist Arthur Eddington once said, "If your theory is found to be against the second law of thermodynamics, I can give you no hope." In other words, break this law and your theory is doomed. So Bekenstein made a bold proposal. Black holes must have their own entropy. And whenever you throw something into a black hole, its entropy must increase. That is, every time it consumes matter, it grows. Just a little. On the outside, it might look like the black hole swallows everything and leaves no trace. But in fact, its surface, the event horizon, is quietly recording every detail. Each time it absorbs something, the event horizon expands slightly, like the pages of a heavy encrypted logbook, storing every piece of information that falls in. Even more astonishingly, Bekenstein discovered that a black hole's entropy isn't proportional to its volume, but to its surface area. It's as if you placed a two-dimensional disk inside a three-dimensional universe, and somehow it contained the blueprint of an entire world. A chilling idea began to form. Maybe the information we think is hidden inside has been written on the outside all along. This was the seed of what would later become known as the Bekenstein-Hawking entropy, a groundbreaking discovery that brought black holes into the realm of thermodynamics. It showed that black holes aren't just lifeless voids. They have heat, they store entropy, and perhaps they evolve. And with that realization, the door was open to the next radical idea, that black holes might not last forever, that they could, in fact, radiate and evaporate. When Bekenstein first proposed that black holes should have entropy, he was only trying to fix a logical hole using the language of thermodynamics. But what he found would change physics forever. But Stephen Hawking went even further. He didn't just accept the idea that black holes, like thermal systems, have entropy. He asked a far bolder question. If black holes behave like hot objects, could they also have temperature? And if they have temperature, could they also emit energy, like a furnace? At first, this sounded absurd. After all, the very definition of a black hole is that nothing can escape, not even light. So how could it possibly radiate anything? But Hawking refused to accept that black holes were completely black. Starting from the principles of quantum field theory, he carefully analyzed the energy behavior near a black hole's event horizon, and he reached a stunning conclusion. Black holes can glow. More precisely, they can evaporate. This radiation doesn't happen because light escapes through the black hole's boundary. Instead, it comes from a deeply counterintuitive process, quantum fluctuations. According to the Heisenberg uncertainty principle, even a vacuum is never truly empty. Space is constantly flickering, with brief appearances of particle-antiparticle pairs. These virtual particles pop into existence, interact, and then annihilate each other almost instantly. The process is so fast it doesn't violate conservation laws, and it usually leaves no trace. But near the event horizon of a black hole, something strange can happen. If a virtual particle pair appears right at the edge of the black hole, one of them might fall in before they can annihilate each other, while the other escapes into space. This tiny imbalance, one particle going in, one escaping, breaks the perfect give and take of quantum vacuum energy. The particle that falls into the black hole carries negative energy. To keep energy balanced, the black hole must pay for it, meaning it loses a bit of its own energy. The escaped particle, meanwhile, becomes real radiation, something that we, in theory, could detect. This is Hawking radiation. And here's what's even more surprising. The temperature of a black hole is inversely proportional to its mass. In other words, the smaller the black hole, the hotter it becomes, and the faster it evaporates. That means tiny black holes possibly formed in the early universe could be hotter than stars, raging, unstable thermodynamic bombs. And that leads to an unprecedented cosmic question, one that physics still hasn't fully answered. If black holes really do evaporate over time and eventually vanish, what happens to all the information they once swallowed? Is it quietly released through the radiation, or is it lost forever in the depths of warped space and time? This isn't a philosophical question. It's a direct challenge to the most fundamental laws of physics. Can information be truly destroyed? If the answer is yes, then the entire foundation of quantum mechanics would need to be rewritten. But if the answer is no, then black holes cannot be what we thought they were. Hawking radiation didn't just redefine the fate of black holes. It threw an entire branch of physics into a decades-long crisis known as the black hole information paradox. Imagine this. We take all the information from human civilization, every encyclopedia, every hard drive, every thought, conversation, and scientific formula, and throw it into a supermassive black hole. Then we wait, watching as the black hole slowly evaporates until it disappears completely. Now comes the big question. Where did all that information go? According to Hawking's calculations, the radiation emitted by a black hole is purely thermal. In other words, it carries no clues about the original matter that fell in. It's just heat, random and structureless. It's like throwing a contract into a furnace. When it burns, all you get is heat and ash. Nothing remains of the words that were on the paper. You can't reconstruct the original document from smoke. And that idea, that information could be lost forever, violates one of the deepest principles of modern physics. Information cannot simply disappear. In quantum mechanics, even if a system undergoes incredibly complex transformations, if you know every detail of its evolution, you should always be able to work backward and recover its initial state. This idea is like the memory of the universe. No matter what happens, the universe keeps track. It remembers. But if black hole evaporation is truly irreversible, if radiation leaks out but the original details are forever gone, then the black hole behaves like a cosmic paper shredder. You see the input, you see the output, but everything in between? Gone. And that, in theory, would mean that quantum mechanics itself breaks down. For a time, the physics world was split in two. One side supported Hawking, arguing that information really does disappear, that it's a fundamental feature of black holes. The other side strongly disagreed. Information conservation, they insisted, is a core principle of quantum mechanics. Black holes must preserve information in some hidden way, we just haven't figured it out yet. This debate lasted more than 2 decades. It became one of the most profound and complex scientific controversies of the 20th century. The black hole information paradox. At first, this sounded absurd. After all, the very definition of a black hole is that nothing can escape, not even light. So how could it possibly radiate anything? But Hawking refused to accept that black holes were completely black. Starting from the principles of quantum field theory, he carefully analyzed the energy behavior near a black hole's event horizon, and he reached a stunning conclusion. Black holes can glow. More precisely, they can evaporate. This radiation doesn't happen because light escapes through the black hole's boundary. Instead, it comes from a deeply counterintuitive process, quantum fluctuations. According to the Heisenberg uncertainty principle, even a vacuum is never truly empty. Space is constantly flickering, with brief appearances of particle-antiparticle pairs. These virtual particles pop into existence, interact, and then annihilate each other almost instantly. The process is so fast it doesn't violate conservation laws, and it usually leaves no trace. But near the event horizon of a black hole, something strange can happen. If a virtual particle pair appears right at the edge of the black hole, one of them might fall in before they can annihilate each other, while the other escapes into space. This tiny imbalance, one particle going in, one escaping, breaks the perfect give and take of quantum vacuum energy. The particle that falls into the black hole carries negative energy. To keep energy balanced, the black hole must pay for it, meaning it loses a bit of its own energy. The escaped particle, meanwhile, becomes real radiation, something that we, in theory, could detect. This is Hawking radiation. And here's what's even more surprising. The temperature of a black hole is inversely proportional to its mass. In other words, the smaller the black hole, the hotter it becomes, and the faster it evaporates. That means tiny black holes possibly formed in the early universe could be hotter than stars, raging, unstable thermodynamic bombs. And that leads to an unprecedented cosmic question, one that physics still hasn't fully answered. If black holes really do evaporate over time and eventually vanish, what happens to all the information they once swallowed? Is it quietly released through the radiation, or is it lost forever in the depths of warped space and time? This isn't a philosophical question, it's a direct challenge to the most fundamental laws of physics. Can information be truly destroyed? If the answer is yes, then the entire foundation of quantum mechanics would need to be rewritten. But if the answer is no, then black holes cannot be what we thought they were. Hawking radiation didn't just redefine the fate of black holes. It threw an entire branch of physics into a decades-long crisis known as the black hole information paradox. Imagine this. We take all the information from human civilization, every encyclopedia, every hard drive, every thought, conversation, and scientific formula, and throw it into a supermassive black hole. Then we wait, watching as the black hole slowly evaporates, until it disappears completely. Now comes the big question. Where did all that information go? According to Hawking's calculations, the radiation emitted by a black hole is purely thermal. In other words, it carries no clues about the original matter that fell in. It's just heat, random and structureless. It's like throwing a contract into a furnace. When it burns, all you get is heat and ash. Nothing remains of the words that were on the paper. You can't reconstruct the original document from smoke. And that idea, that information could be lost forever, violates one of the deepest principles of modern physics. Information cannot simply disappear. In quantum mechanics, even if a system undergoes incredibly complex transformations, if you know every detail of its evolution, you should always be able to work backward and recover its initial state. This idea is like the memory of the universe. No matter what happens, the universe keeps track. It remembers. But if black hole evaporation is truly irreversible, if radiation leaks out but the original details are forever gone, then the black hole behaves like a cosmic paper shredder. You see the input, you see the output, but everything in between? Gone. And that, in theory, would mean that quantum mechanics itself breaks down. For a time, the physics world was split in two. One side supported Hawking, arguing that information really does disappear, that it's a fundamental feature of black holes. The other side strongly disagreed. Information conservation, they insisted, is a core principle of quantum mechanics. Black holes must preserve information in some hidden way, we just haven't figured it out yet. This debate lasted more than 2 decades. It became one of the most profound and complex scientific controversies of the 20th century, the black hole information paradox. But this wasn't just an academic dispute. It struck at the very foundation of modern physics. Because if information can silently evaporate in some corner of the universe, then our entire understanding of causality, conservation, and reversibility could collapse. And yet, it was this very crisis that gave birth to a more radical idea. What if we've been looking in the wrong place all along? What if the information never actually entered the black hole at all, but was somehow stored on its outer surface? This seemingly absurd idea would evolve into one of the most astonishing theories in modern physics, the holographic principle. If black holes really evaporate and take their information with them, then we must confront a disturbing question. Is the universe secretly deleting data? At the height of this crisis, when there seemed to be no way forward, someone noticed something odd, something that had been written down long ago. The Bekenstein-Hawking entropy formula. This formula states that a black hole's entropy is not related to its volume, but to its surface area. That's strange. After all, a black hole is a 3-dimensional object. You would expect its information capacity to depend on how much space it has inside. But the formula says otherwise. It suggests that all the information a black hole can hold is limited by the area of its boundary, not its interior. It's like buying a hard drive and finding out that its storage capacity depends only on the size of its outer casing, not on how many chips are inside. It sounds completely unreasonable, and yet, it's correct. This strange formula, one that looks like someone used the wrong units, would go on to inspire one of the most astonishing ideas in theoretical physics, a proposal so bold it was first seen as borderline madness. What if everything we see in our 3-dimensional universe is actually just a 2-dimensional projection of information? In other words, all the things you believe to be real, galaxies, stars, planets, bodies, brains, even your own memories, might just be the encoded result of some deeper, lower-dimensional structure. What we perceive as solid and 3-dimensional might in fact have no real depth at all. It's like watching a movie. The screen is flat, only 2-dimensional. Yet you see a vivid 3-dimensional world. You see astronauts floating in space. You see spacecraft crashing into black holes. But in reality, it's just light and color projected on a surface. Physicists call this mind-bending idea the holographic principle. Holographic means that the whole is contained in each part, and that the boundary contains the core. Black holes are believed to be the most extreme example of this principle. A black hole isn't a box. It's more like a cosmic labeling machine. It encodes all the information from everything that falls into it, not deep inside but on its surface, the event horizon. It works like a universal QR code. You can't see what's inside just by looking, but with the right decoding method, all the information is still there, not lost, just hidden in plain sight. This means the event horizon is no longer a one-way edge of destruction. It becomes an information wall of the universe, storing every history, every state, and every vanished particle in perfect detail. In a way, gravity compresses the 3-dimensional structure of everything inside a black hole into a 2-dimensional surface, where each unit of area holds a minimal piece of data, a bit of information. As wild as this sounds, mathematically, it checks out. And here's the truly revolutionary part. This might not just apply to black holes. Some physicists have boldly proposed, if black holes can encode information on a surface, why not the entire universe? What if our entire three-dimensional reality is just a projection from a two-dimensional boundary, an invisible cosmic wall? This isn't science fiction. It's actually a mainstream hypothesis supported by many current physical models. Of course, no one has yet found such a cosmic wall, and no one can say for sure whether this is the final truth, but the implications are staggering. What we thought was a three-dimensional universe might, in truth, be nothing more than a two-dimensional projection of information. Everything we perceive as real, galaxies, stars, planets, our bodies, our brains, even our memories, may all be just the encoded output of a deeper, lower-dimensional reality. We see depth, but it may have no actual thickness. It's like watching a movie. The screen is flat, but we see an entire world play out in 3 dimensions. We watch astronauts float through space, spaceships crash into black holes, but in the end, it's just light and color projected onto a surface. This is the core idea behind what physicists call the holographic principle. Holographic means that each part contains the whole, and that the boundaries can encode the full interior. Black holes are considered the ultimate realization of this principle. A black hole is not a box that hides everything deep within. It's more like a cosmic label maker, encoding the information of everything it consumes, not inside, but across its surface, the event horizon. It becomes a kind of universal QR code. You can't see the contents, but with the right key, everything is still there. The event horizon, once seen as a one-way gateway to destruction, transforms into an information wall, a recording surface that preserves every particle, every moment, every history. Gravity, it turns out, might compress the entire three-dimensional interior of a black hole into a flat, two-dimensional information sheet. Every bit of area corresponds to a bit of information. As fantastical as it sounds, this works out mathematically. And what's more, it might not just apply to black holes. Some physicists have dared to suggest that the entire universe might work this way, that our 3D world is a holographic projection from a 2D surface we cannot yet detect. This isn't science fiction. It's a serious hypothesis supported by many theoretical models. Of course, no one has found this cosmic wall, nor confirmed that this is the final truth. But the very fact that such an idea makes mathematical sense has changed physics forever. Since the arrival of the holographic principle, physics has never been the same. It didn't just add a new chapter. It questioned whether we had been reading the book in the wrong dimension all along. And behind this dimensional illusion lies a deeper mystery. If information is really encoded on the surface, who is writing the code? Who or what understands the full script? The black hole, once thought to be silent and sealed, now resembles a cosmic black box. We can't see inside, but we know it holds the universe's most hidden records. And maybe it was never meant to be completely sealed. If black holes don't destroy information, then where is it hiding? What if they're not vaults, but compressed archives? Could we someday decode them, like unzipping a cosmic file? The problem is, we still don't know how the data was packed. What is a black hole truly made of? Does it have an internal structure beyond what we can see? That may be the key to solving the information puzzle. And the first serious attempt to unpack a black hole didn't come from telescopes or particle colliders, but from pure mathematics written on paper. In 1995, physicists Andrew Strominger and Kumaran Vafa achieved a historic breakthrough. Rather than study real black holes in space, they used string theory to construct a highly idealized, but mathematically precise, black hole model. This model didn't mirror our universe. It had 5 spatial dimensions, special symmetries, and exotic matter that exists only in theoretical frameworks. But it was precisely this idealization that allowed them to break the black hole down piece by piece, like solving a cosmic Rubik's Cube. They did something no one had done before. By approaching the black hole from the inside, physicists attempted to calculate the number of its microscopic states. In other words, how many internal arrangements were possible without altering the black hole's outer appearance. Imagine facing a combination lock. On the surface, you only see 3 dials, but what actually keeps it locked is the vast number of hidden combinations behind them. Strominger and Vafa were the first to lift that lid and count the internal mechanisms. The most astonishing part? The entropy they calculated from these internal states matched perfectly with the result Hawking had derived from thermodynamics and gravitational theory. It was the first time in history that humanity, without relying on telescopes or experiments, proved from the inside that the Bekenstein-Hawking entropy wasn't just theoretical. It actually represented a real count of information. This wasn't coincidence. It wasn't metaphor. It was proof of a deeper layer of code woven into the fabric of the universe. Of course, this result came with limitations. Their calculation only applied to highly idealized black holes, ones that exist in a version of the universe with 5 spatial dimensions, supersymmetry, and exotic fields that don't exist in our observable cosmos. Their model was different from the real black holes like Cygnus X1 or the supermassive object at the center of the Milky Way. Still, the result was like a beam of light cutting through the darkness. It didn't answer all the questions, but it was the first step toward understanding what a black hole really is. At that moment, black holes began to seem less like endpoints and more like encrypted archives, books of secrets that might one day be read. Perhaps you remember the original question. If a black hole can be fully described by only 3 numbers, mass, spin, and charge, then what happens to all the information it devours? Now we finally have a hint. It wasn't destroyed. It was hidden. It might be encoded on the event horizon, entangled in quantum fluctuations, embedded in the temperature curve of Hawking radiation, or possibly even beyond our current understanding of dimensional space. A black hole isn't just a gravitational endpoint. It may be the universe's way of compressing vast amounts of information into a tiny. On the surface, we only see the mass, the spin, and the charge. But inside lies a rich and complex archive sealed in a language we have not yet deciphered. And the boldest suggestion? Maybe the entire universe follows the same principle. Perhaps what we perceive as a 3-dimensional world is merely a projection of 2-dimensional information, spread across a higher dimensional space. What we see, galaxies, stars, even our own bodies, may not be reality itself, but rather the result of encoded rules playing out on a cosmic surface. It sounds insane, but it's precisely this kind of idea that pushes human understanding to its edge. A few centuries ago, people couldn't imagine the existence of dark stars. Just decades ago, many doubted black holes were real. And now we're beginning to believe that the universe itself may be a kind of computation, a memory system, a grand simulation we've only started to decode. So what is a black hole, really? Is it a graveyard that consumes everything? A merciless delete key of the cosmos? Or is it something more, a vast, intelligent bank of information? For the first time, we're beginning to understand that perhaps the universe wasn't built for us, but maybe, just maybe, it never intended to keep all of its secrets hidden. We are inching closer to the core of the mystery behind black holes. And at the end of this journey, the greatest discovery may not be the truth of the universe, but our own relentless desire to seek it.